My name is Brighton Godfrey. I'm a graduate student at UC Berkeley, working on, at the moment, internet routing. And I should acknowledge my co-authors as well, Matt Caesar, Ian Hacken, Scott Schenker, Jan Stojka. So it's well known that instability in internet routes can cause trouble at several layers, both the control plane and the data plane. So on the control plane, processing BGP updates can use, at some routers, a significant fraction of CPU cycles. And this was, BGP update churn was recognized as one of the challenges for scaling the routing system. On the data plane, BGP update processing is correlated with degraded path quality. So one study, for example, showed that BGP, rather than congestion, causes the majority of packet loss bursts. So we'd like to address these problems with CPU utilization, which makes routers more expensive or delays convergence, and also with degraded path quality, by making paths more stable. And I'll describe our approach, which we're working on at Berkeley. So there is already a widely deployed technique for improving stability on the internet, and that is route flap damping. Unfortunately, flap damping comes with some pathologies and reduces availability, and I don't think I need to go into detail about this since we had a live demonstration on Monday, as I understand it. And this has led the RIPE route working group to write that the application of flap damping in ISP networks is not recommended. So in addition to those problems, flap damping actually only helps for the outliers, the very unstable routes, those whose instability surpasses some threshold. And so it does nothing for the routes which are only moderately unstable. So we're going to take a different approach, not an entirely unique approach, and that is, given a choice between routes, we'll select routes that are less likely to fail. So we'll refer to this technique as stable route selection. So comparing this to flap damping, in the route flap damping philosophy, you shut off the bad routes. In SRS, we will always pick a route if one is available. However, when we're given a choice, we'll prefer more stable routes over less stable routes. Taking this approach is going to lead to a number of challenges. So first, we have to be able to locally infer the relative stability of paths in order to make a good decision, or at least an educated guess, because we don't want to modify the routing protocol and send additional information. There's also an issue of dependence. So path selection on the internet is a cooperative process among the ISPs. So if only a few ISPs are optimizing for stability, their benefit may be limited if none of the other ISPs are interested in doing that. And finally, perhaps most importantly, taking the approach of optimizing stability by using flexibility in route selection is going to lead to trade-offs, because that flexibility is also used to optimize for example, path length. So in the rest of the talk, I'm going to discuss the design of stable route selection, how we implement it, and then evaluation based on simulation, highlighting these three challenges that I described, and then I'll conclude. So in the internet today, if you have a choice between multiple paths in BGP, you follow a decision process like that one, what I'm showing here. Actually, this is a slightly simplified version of what happens in reality. So if you have two paths and you're choosing between them, you'll first pick the one that has highest local preference. Second, if there's still a tie, you pick the one with shortest path length, and so on. So what we're proposing to do is to replace some of these steps with a step that will optimize for stability, preferring paths that are less likely to fail soon. Now, in principle, you could do this at any step of the decision process, and in some routers, it's actually done already fairly low in the decision process. The approach that we're going to take for this talk is to replace path length with a heuristic for stability, which will pick paths at the AS level, and then we'll return to the other steps in the decision process. So it's important that we use a heuristic that's simple and efficient so that it can be implemented on a router. Although we've investigated several, what I'll use in the results here is the following. So first, stick with the route that you're using as long as it's still available. Second, if you're forced to switch, then pick the available route with shortest path length. And finally, if there's still a tie, pick the oldest route, one with longest uptime. Now, in the simulations I'm going to show you, we actually have a simplified environment where we have only a single simulated router per autonomous system. So this results in a somewhat simplified decision process that's here. I won't go into detail about it. Okay, so let's see how these different strategies perform. So I'm going to show you an evaluation based on an event-based simulator of BGP fed by a number of measurements of the internet. So we have a topology at the AS level, as I said, with one simulated router per autonomous system, so about 21,000 simulated routers. Local preferences inferred from customer-provider-peer relationships, and a trace of about a year in length of AS adjacency failures inferred from route views. And the primary metric that we're going to be evaluating is interruptions in terms of measuring stability. So an interruption is a change in a route or a withdrawal of the route, basically a flap. So interruptions are really only a proxy for metrics that we actually care about, namely load on routers or packet loss. But using interruptions allows us to scale the simulator to a very large size. Okay, so let's get right to the results and see how well we can do with this kind of an approach. So what I'm going to show you is the mean rate of interruptions per month per source destination pair, and also the loss in availability relative to standard BGP. So standard BGP, no flap damping, gets about 26 interruptions per month in this environment. And of course, no loss in availability relative to itself. Turning on flap damping, you do get a significant improvement in stability. But this comes at the price of measurable loss in availability as well as the pathologies that I described. So interestingly, stable route selection can perform even better in terms of the mean rate of interruptions without ever turning off a route. So it has the same availability as BGP without flap damping. Now combining these techniques, flap damping and SRS, you can do even better, which demonstrates that to some extent they're complementary. Now interestingly, if you start with flap damping and then turn on stable route selection, not only do you get an improvement in stability, you also get a slight improvement in availability. And the reason is that SRS is picking more stable routes, which triggers flap damping less often. Okay, so these results that I've shown you are based on a full deployment. That is, all ASs running these strategies. So what happens if we have only a partial deployment? So this plot shows in the blue line the interruption rate of standard BGP. And here's the point that I showed you from the previous plot. At full deployment, we get about a factor of 5 improvement in stability. And we can fill in the chart along the x-axis, varying the fraction of autonomous systems that are running SRS. And particularly important is the point along the left, at the left, which corresponds to the improvement that the first adopters would receive. So whether 44% is significant is perhaps debatable, but this point is actually the average over all autonomous systems, and some perform much better. For example, the tier 1s, shown here in red dots. I'll explain this plot by example. So each one of these red dots is a particular tier 1. So AT&T, for example, according to this simulation, gets about 17 interruptions per month in standard BGP. And this could be reduced by a factor of 3.5 by turning on, if AT&T and no other ISPs turned on stable route selection. So this shows that the tier 1s benefit significantly more on average than the other ISPs when unilaterally running stable route selection. And this is because they have more flexibility. Which brings me to the final section of the evaluation that I'll talk about. So flexibility is something that's also needed or useful for performing load balancing among providers or satisfying business relationships, minimizing path length, and so on. So the question is, what is the trade-off with these other objectives? So at the high level, we have kind of a continuum here between either more flexibility for stable routing versus more flexibility for other objectives. So standard BGP gives no flexibility to stability. And we've already seen that if we satisfy business relationships and give the rest of the flexibility to stable route selection, we can get about a factor of 5 improvement. And the big open question is, how much improvement do we get with a realistic amount of flexibility, realistic traffic engineering, and so on? And this is something that we're unfortunately unable to quantify with the data we have, because it involves private policies. And so we're very interested in collaborating with industry folks to quantify this. What we can quantify with this data set that we have, however, is path length. So this is a CDF of path lengths in standard BGP. And that's what it looks like with stable route selection. So interestingly, path lengths really don't increase very much at all, only about 4% more on average. And this is for several reasons. First, we're taking into account path length as a component of our heuristic. And also, actually, in this environment, path lengths couldn't get much longer due to the constraints of the customer-provider-peer relationships. Okay, so let me summarize what I've told you. So I've described stable route selection, which is an approach to use flexibility in path selection in order to optimize for stability. So our preliminary results show that it is possible to make the internet significantly more stable using this approach without impacting availability and with very low stretch, that is, very low increase in path length. What we're working on now is a implementation of software router and testbed-based deployment in order to get more realistic performance results. Now let me conclude with one of the main reasons that I'm here at NANOG. I've already got some great feedback from many of you, but we're interested in a number of questions, and here are some of the main ones. First, how useful in practice is stability for you as operators? Second, what would be the barriers in practice to implementing and deploying a scheme like this? For example, is non-determinism in route selection something that would be very detrimental? And finally, if those barriers could be overcome, how much flexibility would remain for stability? This is something I'd like to quantify, for example, in terms of the average number of routes available, route options available. So that's it. I'm very interested in feedback on any of these questions or other comments you have, as well as collaborations with operators in order to make this work more practical. Thank you very much.
Okay. Folks, I'm going to ask if you have questions that you do it either after the session's over or just take it up offline out in the hall. We're running a little behind schedule, and I'm trying to catch us up a little bit here. So thank you, though. Interesting work.